Okay. Remember, don't say anything dumb, right? Because it's going to get recorded now. So you have to give only right answers, only correct answers. Otherwise, the whole world will know your disembodied voice. I'm joking. Don't worry. 5 people will watch this. It's not a big deal. All right. All right. So we're back. I'll give back your exams at the end. Otherwise, it's hard to take notes when you're crying, right? You know. I'm joking. All right. But anyway, let's get started. Let's get started with prayer, and then we'll continue on through chapter 4 there. And Lord, we just thank you for another day. Lord, we just thank you for another opportunity. We just thank you for another blessing, Lord. We thank you for the air we breathe, and everything that you've given us, Lord. Just help us to be eternally grateful for these things, Lord. Help us not to take the gifts that you've given us for granted, Lord. Show us how we can share these gifts with others. Show us how we can share these things with the people around us that don't know you, Lord. We thank you for the relationship that we have with you, Lord. We pray that you strengthen us. We pray that you give us faith to continue to walk with you, Lord, and give us the courage to stand up. We pray all this in your name. Amen. All right. So, chapter 4, we were just talking broadly about the different reactions that we're going to kind of see. There's really only a handful of these that we're going to really drill down into. The exchange reactions is going to be one of them. We've kind of done combination reactions already. When we were talking about how we can form ionic compounds, right? It's just a game of balancing charges. And we're going to play that same trick again, but now we're going to learn it more with covalent compounds, right? So we're going to have to learn another, let's say, contrived charge distribution analysis. Boy, did that sound scientific, right? You guys impressed?
Yeah.
Thank you. That's the right answer, right? What I mean is we're going to have to learn a new way that we have of tracking electrons. Because what does electrons? What does chemistry? Electrons. There we go. All right, we got it. Answered my own question. Okay? So we're going to learn a new method in this chapter also. It's going to be referring to oxidation states. And that's going to help us kind of determine how some reactions proceed and how we know or how we can expect certain compounds to form as we go through all these different reactions. Okay? And there's going to be one more that's kind of on this list, but should kind of have its special place also. We're going to talk about neutralization reactions, acid-base chemistry. And we're going to mention acid-base chemistry very soon. And then it's going to disappear off the radar. It's going to come back for 3 chapters in Gen Chem 2. And then it's going to come back for all of organic chemistry. And it's going to come back for what? All of biochem? Yeah, right? So all of biochemistry also. So it's oddly placed, but I try and stick with things in the book as they are as closely as I can to make logical sense of it. So acid-base chemistry is extremely important. So we're going to learn neutralization reactions, and we're going to learn how to name acids. Okay. So we'll talk a little bit about that. But anyway, so this was kind of where we left off. This is a summary here of the different reactions that we do have, and I believe when you guys go through and do the copper reaction in lab, is that what you have to do? Like the copper reaction, I believe? Then you guys will be having to name some of this stuff and figure out what reactions are going on. So. All right, we already talked about balancing reactions, right? This is just kind of a callback to what it is, blah, 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 blah. We got that. All right, so let's talk real quick about our solubility rules. Now, to get something done, to get a reaction going, the best way to do this is everything has to be in the same phase, right? So what I mean is this, right now, right, you guys have your notebooks on top of your desks, right? Are they reacting with each other? Well, no, right, and if you mix 2 solid chemicals together, you just put one on top of the other, most of the time they're not really going to react because the molecules in there aren't really, in contact with each other. If you remember back in chapter 1, back when life was easy, right? Way back in chapter 1. Right, we talked about kinetic molecular theory, right? And we just related that to how molecules are in motion, how atoms are in motion, and all this kind of stuff. For a reaction to happen, and we'll talk about this more in the second semester, right? We have to deal basically, I think they're referred to as collision theory in this book. Basically, we have to do a bunch of car crashes, is what it is, okay? Two atoms have to come together at the right speed, at the right direction, at the right magnitude, at the right time, in the right space, and then a reaction can proceed, right? So we basically have to start mixing things up and putting things together, and if all these criteria are met, how are the movies?
You only watched the first.
You only watched the first one. Oh, I heard you were up late or something. Right? But anyway, if all these things come together at the right time, place, speed, energy, blah, 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 then a reaction happens. And so the reason why we have to put everything into solution is because when things are in the aqueous state, or when they're in the liquid state, if you want to think about it like that, then we can start to mix things up, right? We can stir things with a stir rod or a magnetic stir bar. We can heat things up, we can boil the water, all these kind of things to help these reactions proceed. It's the same reason why you mix the flour and the butter and the eggs and all that stuff and then put it into the oven to bake it, right? We need to have energy to get the reaction to go. And we'll talk about that a little bit in chapter 5 also, right? And so what we have to do is then be able to dissolve our compounds into water or whatever solvent we are going to use. And for our purposes, it's pretty much exclusively going to be water, right? Now, what we talked about in the beginning of this chapter is that ionic compounds are soluble in water. But what did I warn you guys about? I lie to you guys constantly, okay? I can't help it. When you become a professor, what you try and do is you try and obfuscate all this information, because if you guys knew it all, then you wouldn't need me, and I wouldn't have a job, right? Is that, no, that's not what it is, okay, right? What I mean is, not all ionic compounds are going to be soluble in water. Now you guys already know this. Like I do? Yeah. We'll talk about how, some examples of how you guys already know this and these kind of things, right? So what we have to learn are these solubility rules. Now, here's the good news, okay? The good news is you don't have to memorize these solubility rules anymore. No, we want to memorize more stuff. Okay? But you do have to understand how to use them, right? Now, your solubility rules are always going to be on that data sheet that I give you guys there. There's a little table of it at the back, so make sure before you guys come to the exam, you take a look at that. It's posted online. You guys are welcome to access it whenever you want, right? Make sure you take a look at that sheet and understand how to read that table and be able to apply them, because you are going to have to use it, okay? You are going to have to use it. You are going to be able to need to predict whether things are soluble or not, okay? So I've kind of taken that table and broken it down into some of its components here. Okay, so first of all, I'm going to ask you guys a very important question. What is an ionic compound? Go ahead. Somebody. Yeah, go for it.
The ones that are inorganic, and then also the metal, non-metal.
Mm-hmm. So they're defined in a couple different ways. The broadest definition is we have a cation and an anion, right? We have cationic species, we have anionic species, right? It's a compound made up of ions. That's an ionic compound. Well, it's a stretch there, but right, that's the name, right? Okay? We call them metals and non-metals is kind of what we refer to, but that's kind of maybe a more narrow definition there, okay? So if we just look for something that's positive and something that's negative, then that comes together, okay? So with respect to ionic compounds, every ionic compound that has ammonium or a group 1A metal. Now what is ammonium? I know it's written up there, right? NH4, 1 plus. It's one of our special what? Polyatomic ions, okay? Do your polyatomic ions make ionic compounds?
Yes.
Yes, right? Because they are ions, right? Now what's special about ammonium in terms of the polyatomic ions? It's the only positively charged one. Pay attention though. We have nitrogen and we have hydrogen in ammonium. Is nitrogen a metal? No. Is hydrogen a metal? We'll say no, right? It's a weird one, but it still makes an ionic compound. You guys get what I'm saying with this? So be careful when we define things as a metal and a non-metal to make an ionic compound. We're just looking for charged species, okay? But anyway, any ionic compound with a group 1A metal, your lithium, your sodium, your potassium, your rubidium, cesium, right? Where are your group 1A metals? All the way on the left-hand side of the periodic table, right? Any ionic compound that has those will be soluble. So when we put those into water, they're going to break apart. They're going to dissociate. Take a look at your notes from the beginning of this chapter. We said that ionic compounds are going to dissociate. The cations and the anions are going to separate, okay? Anything that has nitrate or acetate is going to be soluble also. Got it? So when we start to look for, is something soluble, and you see ammonium, the assumption that we make is that it's going to be soluble in water. It's going to completely dissociate into its constituent ions. Okay? Most. Now we get into the kind of the vague part here. Most ionic compounds that have chlorides, bromides, or iodides are soluble. So most chlorides, bromides, or iodides are soluble. With the exception of what? Silver, mercury, and lead. Okay? So if you see silver chloride, it's not going to be soluble in water, right? It's not going to be soluble in water. I should technically say silver 1 chloride, right? But would we expect silver nitrate to be soluble in water? Silver 1 nitrate. Well, right?
Yeah.
There's my pen, right? Ooh. There's my silver 1 nitrate. Is that an ionic compound? We've got a metal, we've got a non-metal, we've got a cation, we've got an anion. We see that it's got nitrate in there, and what do the rules say? Rules say that all nitrates are going to be soluble. So do we expect silver 1 nitrate to be soluble in water? Yes. Got it? Now, what I should have said at the beginning, but I'll say it here now, there's an order of importance for this, right? The all rule trumps the most rule kind of thing, okay? So if you see something that falls into the all rule, we can go by that. All right, sulfates, SO4 2-. These are mostly going to be soluble, except for calcium, strontium, barium. Oh man, that's so random. Why do they pick these random atoms that are insoluble with sulfates? What's Ca? Calcium. What's Sr? Strontium. What's Ba? Barium. Which are insoluble with sulfates? Oh, they're all what? In the same family, right? The same. What do we know about things in the same family? They're going to have similar properties, similar reactivity, right? Now we notice it doesn't include magnesium, although, wow, like go to previous statement about lying. These are rules, right? But the rules are kind of like the pirate code, right? More like guidelines, okay? So we'll go by the rules for what we need to in this course, but understand that there's other aspects going on also. So calcium, strontium, and barium are going to be insoluble with sulfates. And we also got our buddy lead over here, right? But if you'll notice, right? If you'll notice, lead shows up in both of these conditions here. Lead is just kind of a pain in the butt, okay? It doesn't want to be soluble with the halides. It doesn't want to be soluble with the sulfates. Okay. But these all exist in the same family. Insoluble things: phosphates, carbonates, oxalates, oxides, sulfides, hydroxides. We got to be careful with some of these. Okay. But especially up at the top, what do we notice? We got phosphate, carbonate, oxalate, oxide, sulfides. These are high-charged ionic, anionic compounds, or anionic species. Okay? The higher the charge you do, the more difficult it is to dissolve something, because we're basically putting two big magnets together, right? Remember, negatives attract positives. If I've got a -3, right, that's a big magnet to attract positive things to it. So it's difficult to pull these things apart sometimes. Okay? And that goes back to explaining some of these other properties that we discussed with ionic compounds about their melting point and these kind of things. Right? But remember, right, there's an order of importance here. And so what I mean is this. Phosphates are typically insoluble, although if I have sodium phosphate, we would consider that soluble. Why? Because what's the first rule that we learned? All group 1A metals, right? And your ammonium compounds are going to make soluble compounds. Does that make sense? Now again, I don't need you guys to memorize this, I need you to understand it, right? The understanding part comes from being able to follow the rules and know that the all rule trumps this rule here, right? Be careful, there are some slightly soluble hydroxides. And if you notice, it's our buddy strontium, barium, and calcium again, right? So we see these kind of repeated patterns of weirdo solubility things coming back in, okay? And we can play the same trick here: magnesium, calcium, and barium, right? It's all that group 2A metals. They just behave a little bit strange, okay? Now I can read your mind. And in your mind, you guys are thinking, who cares? Right? So we're going to use these for precipitation reactions is what it is. We're going to have to use these solubility rules to determine whether a precipitant forms or not, okay? So we're going to have to check whether something is soluble. If it is soluble, we're going to combine it with other ions and see if something insoluble precipitates out, okay? So whenever there's a question in the book, or if you're watching a video or any of this kind of stuff and talks about, we're going to do a precipitation reaction, or they might call it exchange reactions, we're going to have to be using these rules to figure that stuff out. That's what it is, okay? So, at the top there, that's a typical question that gets asked. It says, if we make a solution of silver 1 nitrate, potassium chloride, what products would form, or what would precipitate out, or what would happen? Any of these types of indications that say, hey, use your solubility rules here, right? So we see a nitrate, those are soluble, right? We see a chloride, those are soluble. We see a potassium, it's soluble, right? We check our rules with this stuff, okay? And what's important to pay attention to when you're answering these questions is, make sure you guys are indicating anything that is insoluble if it does precipitate out. Now I'll walk you through the steps on how to get this answer in just a minute. I'm just going to introduce a little bit of the ideas here first, okay? But a precipitate means we mix two aqueous things together in a solid forms as a product. Where are our products? Products are always on the right-hand side of the arrows there, got it? Now the next kind of point here is always kind of vague. I don't really like how they do describe it in the book, but I'll give you my spin on here in a second. Sometimes we form a molecular compound and they kind of talk about water, or sometimes carbon dioxide, or some of these kind of things in there. That's fine. This specific reaction is actually an acid-base neutralization. And so that's where we're really gonna see this idea come in, okay? What we'll find is if we mix an acid and a base, and I'll tell you guys how we identify those, water is always going to be a product of that neutralization, okay? So we deal with these in almost the same way that we deal with a precipitation reaction, although we do have to identify that they're an acid and a base, okay? And then these are kind of weird. We're gonna try and avoid those as much as we can, just because I don't think we really have the well, let me put it this way, I don't think it's necessary to really figure out whether something's gonna be a gas or not yet, right? So we'll deal with the first two far more than we will with the last one there. Okay. So there we go, precipitations, neutralizations, kind of play off of these ideas here. All right. So, looking a little bit at these precipitation reactions here, when we mix two ionic compounds, or when we mix 15 ionic compounds, the procedure is going to be the same, okay? What we're going to do is we're going to break everything apart into its individual components, the cations and the anions, okay? And then we're going to look to see if an insoluble compound will form from the mixture of those cations and anions. We got to break everything apart if it's soluble, and then put things together to make new compounds. Okay? How are we going to know? How are we going to know what compounds can come together to make new things? Well, let's think about this for just a second here. So, with respect to this problem up at the top here, so let's walk through the line of thought. Hey, it's our buddy silver 1 nitrate. Okay? Step 1, is that an ionic compound? Yeah. Okay. Is it going to be soluble in water? What rule tells us that? Well, the first rule says that any nitrates are soluble in water, correct? Okay? So if it is soluble in water, it will dissociate. Which means it will make a silver ion because it's an ionic compound. Got it? Right? What charge does my silver have? 1 what?
Plus.
1 plus. 1 plus. Okay? And I'll also make a nitrate ion. You guys with me? So they separate out. Okay? Now we got our good old buddy sodium chloride. Okay. Is sodium chloride going to be soluble? Well, it has a group 1A metal, right? So pretty much any sodium-based ionic compound is going to be soluble. Everybody with me on what I did there? So now we got to play the game of make something new. How are we going to play, or what are the rules to make something new? Well, silver has a 1 plus charge. So what's it on the hunt for? Something with a, not necessarily -1, but just something with a negative charge. You guys get what I'm doing here? Put your positives with something negative. Put your negatives with something positive. Got it? So my silver, oh goodness. My silver, right, will come together with my chloride there. Why is it important to have my charge? Yeah. Why is it important to have my charge? That's one reason. What if my silver had a 2 plus charge? Then what? I would need 2 of my chlorines there. You guys get what I'm saying? Don't forget to balance your charges. When do you not balance charges? That's right. Never. Right? Balance your charges. Okay? Balance your charges. So make sure you guys understand that. So my silver and my chloride come together. My nitrate and my sodium come together, right? So sodium nitrate, silver 1 chloride. Oops, I'm going to do that in green. Okay? Those are my new compounds. What do I have to do with those new ionic compounds? Check my, your charge is always important to check that. What else? I'll give you a hint. It's these rules, they're based upon solubility. We'll call them the solubility rules. Right? So remember, that's how we started this. We identified ionic compounds, step 1. Step 2, we asked, are they soluble? Using our rules. Okay? Step 3, if they are soluble, we broke them apart. Step 4, we brought new cations and anions together. And what was that? Step 5 is the last one, right? Step 5 is check solubility rules for my new compounds. Okay? That's not too bad, right? Again, we've got a couple examples coming up, okay? So we could play the same game down here, but I already gave you guys the answer. Potassium nitrate and sodium chloride. If we mix those two together, nothing happens. Because everything that gets formed will remain soluble in solution, so nothing will precipitate out. If everything is soluble, what's going to precipitate out? Nothing, okay? So we got to be careful. You never know when jerk professors might try and trick you guys, right? And the answer is no reaction. I'll keep an eye out for any jerk professors in the hallway, right? So, okay. Is it extremely important to specify the state that everything is in?
Yes.
Yes, because otherwise how are you going to tell me that something precipitated out? Well, you guys see when it turns into a solid, right, this precipitates out of solution, okay? And I think you guys have a lab also where you guys will deal with the precipitation stuff, or, you know, this qualitative assessment. Cool. All right. So there's another example up there. And don't forget to balance your equations while you guys are going through with this also, okay? I'll give you guys the answer for that one. See if you guys can work through that problem better. Yeah?
Right, so we know that you form precipitate when one of the components is not so soluble.
Yeah. Yeah. So an aqueous solution of sodium sulfate is added dropwise to an aqueous barium nitrate solution. Will a precipitant form? What in the world do we need to do first? Take the blah 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 into the chemical equation, right? Write out your chemical equation. guys. Charges, charges. What is sulfate? SO4. 2 minus, right? 2 minus. It's not any 2 plus. There's 2 and 8 pluses. There's 2 and 8 pluses. Put 2 up front. And then put a plus. Does that make sense? Because that's what that tells me. There's 2 sodiums. Right? These are independent atoms from each other. Yeah, we'll just be very careful with your stoichiometry, right? How many sodiums do you have? Is it one? No, I just said you had sodium sulfate. So up in blue there is what I'm asking you guys. Sodium sulfate, Na2SO4, right? Don't forget your charges. Don't forget your charges. Plus barium nitrate. Barium has a +2 charge, nitrate has a 1 minus. So we have to make sure we've got 2 of our minuses to balance out the 2 plus. Okay? So now that we have that written out, we go and check our rules. Right? Are these 2 compounds soluble in water? Now we've got sodium sulfate. Sodium's a group 1A metal. Anything, right? Anything with a group 1A metal is going to be soluble in water, right? Barium nitrate. Oh, that's interesting, right? We got our good old buddy barium there. Remember, barium is some of those exceptions start to creep up with barium, right? But what else do we have with it? We've got our buddy nitrate. And nitrate is in the first rule that says anything with nitrate is soluble, right? So sodium, it's going to be soluble. Nitrate, it's going to be soluble. So watch, okay? Let me change colors here so we can just kind of play the same game here, okay? Look, what happens when you break apart sodium sulfate? 2 sodium ions, right? Got it? How do I know that there's 2 sodium ions? Well, sodium always has a 1 plus, right? And I know I have to have 2 of them for the 2 minus. But how else do I know? Well, it's right here in the formula, right? Okay. Do we break apart our polyatomic ions? No. Leave them alone, okay? They're special. They'll stay as a unit, okay? Break apart the barium. Yay, plus 2 of our nitrates. Got it? It's important to recognize that we have 2 of this stuff in here. What game are we playing? It's the stoichiometry game, right? Balance, 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 balance. Okay. Now let's make something new. We'll mix some sodium, right? Some of our nitrate. And we'll mix our sulfate. Some of our barium. Cool. And we'll see if any of these will precipitate. So let's write out those new compounds. Looks like we will make 2 sodium nitrates. It looks like we will make 1 barium sulfate. going to pause and be very serious for a second. If you guys don't know how to get your charges, you don't know how to write those equations and formulas yet, big problems, okay? We're gonna be writing this stuff, we're gonna be doing stoichiometry, we're gonna be using all this stuff pretty much now until the end of any of your chemistry sequences, no matter where it might be. Okay, we're gonna be able to do all that kind of thing. So please make sure that if you're having problems with it, come see me, or do whatever you guys need to do, right? I know I'm a scary guy, that's why we got Laura over there to help you guys out also, right? So please, 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 if you guys are having problems with this, fix it, okay? Not tomorrow, not after lunch, right? Everyone can come up with 15 excuses not to do something, right? What you need to find is one reason to do something. Excuses aren't gonna get you guys anywhere. Reasons to do something for them, okay? So get it done, right? I want you guys to be successful here. All right. So now that I'm sorry, you had a question.
Yeah, why is it that for Na2, when you break it up, you put the 2 in the front?
Because I have 2 sodium ions, right? It'd be like if I broke you apart, you'd have 2 legs, right? So I'd say 2 legs, not leg 2, right? Make sense?
Yeah.
Okay, so now we play the last game. We check if these are soluble or not. Well, we've got sodium, we've got nitrate, those are both rule number 1, so that's gonna be soluble. We got barium and we got sulfate, right? What does our rule about sulfate say? Most sulfates are soluble, right? Except what? Calcium, strontium, and barium, right? So is this soluble? No. What does that mean? That means it will form a solid. It will form a precipitant. So if we put all this shenanigans together, let's see, I did that in red. So I said sodium sulfate, aqueous, right? Plus barium nitrate, aqueous, goes to form barium sulfate, solid, plus 2 sodium nitrates. Okay. I like it. There you go. Ta-da. Now every time you see a precipitation reaction, just repeat those steps, okay? Check the rules, write the equation, break them apart, put them together, check the rules, okay? Yeah, what's up?
The sodium nitrate at the end and the products,
Yeah.
is that in an aqueous or what?
Oh yeah, thank you. Yes, I forgot that. Good call, aqueous. Now that's important to think about. What is this telling us here? That in solution, we still got the sodium nitrate floating around, right? It didn't precipitate out, it's still an ionic compound, it's still dissolved, right? Okay? So we mix these 2 together, something precipitates out and everything else gets left behind. Got it? Not too bad, right?
Wait, so if it changes to a solid, that means that there's a precipitate?
Yep.
Okay.
Because if it's not in solution, if it's not aqueous, if it's not dissolved, then it's gonna precipitate out. Right? All right. All right, so see what you guys can come up with here. And go ahead and write out the equation like we did for the last problem there. So we're mixing silver nitrate and potassium chloride. So see if you guys can write out your precipitation reaction for us. And then we'll come back and we'll add an idea on top of it. silver nitrate plus potassium chloride goes to make what? Hmm. It's not silver, it's silver ion. It's not silver in its elemental form. Right? We're dealing with ionic compounds in this case. I feel that didn't answer your question. So maybe I didn't understand it. What are you asking then?
Why would the ion not be?
Why does it stay in, why does the ion stay in solution?
Yes.
Okay, I would say that the best answer for that is that the interactions made between the ion and the water are favorable to a manner that would prefer to stay in solution rather than precipitate out. What I mean by that is this. When you dissolve something, you trade one set of interactions for another. You traded interacting with the nitrate, how it started out, to with the water ion that it gets dissolved into. And it just so happens that silver and water make enough good interactions that it's better than when it interacted with the nitrate. Now, we haven't talked about how we know that, right? That's something that's coming up, right? But the answer to your question is, I guess maybe what your question is coming down to is why in the world would this happen to begin with, right? And we'll talk about that in chapter 5 when we deal with the energy of things.
Okay. So
Everything in the universe needs to have a
I
purpose.
guess we're not expected to know that this is.
Oh no, you're expected to know that. That's based off the solubility rules. Your question, how do I know that this breaks apart into that? So, okay. Top line right up there. Soluble ionic compounds fully dissociate. Mm-hmm. And the first rule says anything with nitrate is going to be solid, right?
Okay. All right, thank you.
Mm-hmm. All right. So silver plus nitrate plus potassium plus chloride, right? So these are our players, okay? So now we need to bring the pluses and the minuses together. Okay, so we'll bring those, and we'll bring these together here, right? Good? I kind of wrote myself in the form here. I didn't leave too much space, but we can bring it together, it's fine. So, what we'll do then is, this will make, let's see, purple, right, it will make silver chloride, and in red, potassium nitrate. Good?
Why did they swap it all? Why didn't they just stay together?
Yeah, good question.
Okay.
So the answer is, I'll let you know in about 1 or so chapters. The answer is there has to be a reason for this to happen, right? There has to be some kind of driving force, and it'll take going through the second semester of Gen Chem to get another answer for you, right? So at the end, so the simplified say because energetics, there's a driving force to do that. It's a better compound to make from the molecular perspective. Now that's a bullcrap answer. I'll go and tell you I'm lying to you, but that's the best answer at the moment, okay? All right, anyway. Everybody good on that? So we broke things apart, we bring new things together. We have to do what? Check, right? Check our rules. What do we know? We got silver chloride. That's okay, right? All chlorides are soluble, right? Hmm? Oh, most. Oh. I must have misread my chart. What does the chart say, or what does the table say? Most chlorides are soluble, with the exception of what? Silver and what else would say, mercury and lead, right? So what do we make? Silver chloride, right? Is that gonna be soluble? Nope. So that's gonna precipitate out. What about potassium nitrate? We got a group 1A metal, always gonna be soluble. We got nitrate, always gonna be soluble, right? So let's string this all together. Here's how it's going to look. I'm just gonna rewrite some things to give myself some space. Ag, 1 plus, aqueous plus nitrate, 1 minus, aqueous, plus potassium, 1 plus, aqueous. Tired of saying that word, aqueous. Make AgCl somewhat plus potassium. Everybody with me on this? Why? Why did I write it like that?
Because they're both metals, they don't go together, I'm sorry, they're both, the one that means that they both give, right? No, or not. I got it wrong, never mind.
It's okay, it's okay, it's okay. Why did I write it like that? Yeah.
Because as a product, and it, at that point, you disassociate from each other.
So just because it's a product, it's dissociated.
A product where precipitate forms, meaning.
Well, this precipitated, this didn't, right?
So those dissolve.
What do you mean?
They bonded with.
You're walking around the answer. You're very, why did I separate these out over here? I think it's because soluble ionic compounds might fully dissociate in water. You guys with me on this? Top line, top line, top line. Is this a soluble ionic compound? Yes. Is everything still in water? Yes. So these are dissociated. You guys with me on this? I don't care if it's on the product side or not. It didn't precipitate out, so it stays in solution. Does that make sense? If you don't precipitate, you're part of the solution.
Did it jump up? It was all in water?
Yeah. Mm-hmm.
You're right about that.
Sorry. No, go ahead. What's up?
You're saying unless like it's precipitate out, then it didn't still have to be associated?
Yeah, because it's still, everything's in water, right? Remember, that's the assumption that we make, right? These are solubility rules for ionic compounds in aqueous solution. As soon as we change solvents, we have to kind of throw the rules out, for the most part. Yeah,
Why don't we write the water in there?
we do.
Okay.
Water is our solvent, right? It's not part of the reaction, so to speak, right? Because otherwise we would say this and water, 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 this, right? Everything in there would have water. So it'd be like writing a constant in a mathematical formula. And if it's everything, we can just cancel it all out. Which is a good segue into asking a question. Right? This is basically just a mathematical equation, right? One side has to be equal to the other. What do you guys notice? Potassium and what? Potassium, right? Chloride and, whoops, I pointed at the wrong one, sorry. Nitrate and nitrate. Does the nitrate change from one side to the other? Yeah, it started green and it turned red. What's wrong with you? Geez, come on now, right? Does the nitrate change? No. Does the potassium change? No. So they're the same on both sides, right? So what can we do? Yeah, just get rid of it. Who cares? Useless. Stupid potassium. You don't do anything, right? Get out of here. Okay? You guys see how those are the same on both sides? It's just like in a mathematical equation. If we have x on both sides of an equation, right, they cancel each other out. Yes? So what are we left with? What's our equation now? Our equation is Ag, 1 plus aqueous, plus Cl, 1 minus aqueous, goes to make Ag, Cl, solid. Yep,
Why didn't we do any of that like separating out in the last problem?
because I'm introducing this to you stepwise.
Oh.
You can go back and do it, right?
Okay,
I'm just trying to give you guys one topic to kind of
okay.
make the meal a little bit easier, right? Eat the elephant, one bite at a time. So this is what would be called our net ionic equation, okay? AKA, this is the thing that's reacting. The silver and the chloride react, the other stuff, who cares, okay? So this is our net ionic equation. This would be our complete or total ionic equation if you have everything written out, okay? So if you have everything written out, that's our complete or total is usually what they call it. Our net is just what goes to form the precipitant. Good? Alright, I think the next slide is a summary of all this stuff. There you guys go, right? That's what you've been doing all along. Alright. There you go. Man, I'm tired of talking. I've already had to work for like 50 minutes today. Oh, God, so tired. Alright, see what you guys come up with. So the aqueous solution of the top two there go to make those two, right? So it'd be the NH4 2S plus the HgNO3 goes to make HgS plus NH4. The top two go to make the bottom two. Well, that's because that's what I'm trying to get them to figure out, right? The solubility rules. Laura, who makes mistakes? Somebody else, right? Well, it's not you, it's everybody, because those are the ones that depend, right?
Yeah.
they're dependent on what they're bound to.
Okay.
So, right, we don't know what that is, but we do know what that is,
Yeah.
right?
Okay, so it's found in this.
Mm-hmm. And how many, so what charge does nitrate have?
It would have 2 minus 2G.
Correct, so what does it mean that has to be?
Each has to be plus 2.
There you go,
Okay.
right, that's all, that's it. That's all you gotta do. HGS, what's that one? What's the name of that guy?
Mercury sulfide.
Mercury,
What's it?
Mercury 2 sulfide, right? Mercury 2 sulfide. So is Mercury 2 sulfide soluble or insoluble? So we're gonna take a look at our rules, and what does it say?
No sulfide.
So take a peek. Scrolly. Right? Where is it? There it is. What does it say? Oh, that was crappy. Right? Sulfite salts are insoluble, right? Insoluble. Back. That's going to be our solid then, right? 2NH4, 1 plus 2NO3 minus. Good. So there's my complete equation, my complete ionic equation. To get my net ionic equation, what do I have to do?
Look at all the things that don't do anything.
Cancel out things that are on both sides. Now pay attention here when you guys start to cancel out, okay? When you guys start to cancel things out, we have 2 ammoniums over here, right? We have 2 ammoniums over there, right? So 2 is going to cancel out 2. Now the reason why I say that is because sometimes you might have an unequal amount, you might have 3 ammoniums over here and only 2 over there, right? So just be careful how many of you guys are canceling out or balancing out. Those are somewhat more rare occurrences, but it's something to pay attention to, okay? And there we have our net ionic equation then. I will leave the last one for you guys to name these things, because practice, right? Good? Good. All right. Just enough time for this stuff. We'll know everybody's name, and thank you, Gabriel, for still having your name tag out. So, and make it a little bit more difficult. What's the last name? Actually, I do have them in alphabetical order today. Let's see, what's the last name? Thought of another S. What's the last name? The rare, right? That is kind of Trying to put names and faces together. Got it. I know your first name now. Kaylee, and what is it last one? Chaylee, I apologize.
Do you know her first?
Well, actually, it's not, that isn't actually your first name though, right? Last name. Vanish? Vanish with a D, gotcha. All right. Last name.
Mine wasn't bad. Nope. Glasses.
Yeah, let's watch that. Oh, okay. So I'm just gonna give you a zero. I'm just gonna give you a top. And you're Isaiah. Sorry, what? Yes.
The only thing with the practice.
Oh, I'm sorry. I apologize, I saw sorry about that. What?
I said no online. Oh my god, I went so much better than I expected. I thought this was
I actually gave yours to Isaiah, so I apologize. So, I apologize for that. Go ahead and get me fired, I guess. Fired, that's right. You used to sit there, though. You can, you change it up. Okay. Nah, don't worry about it. Just say it's melody. Come on. Nope. All right. Like I know you're here. All right. Yeah.
You guys do.
If not, I'll double check as soon as I'm done lecturing. Yeah, they'll be there. The limiting factor is, here's me passing out exams. Passing out exams, the video, all right.